Hi guys. Yesterday in one of my videos I received a comment requesting that I go over the May 2025 Unit 5 test, and I decided to do it. So here we are. We're gonna discuss this paper, and let's start by noticing that there was a typo in this test. And I'm gonna come back to this once we go over that material. So let's get started. This is the Unit 5 test of 2025. Okay, it was given last June, so a few months ago. I was able to find it online. I hope this is not a problem for Pearson and Edexcel International tests. So I mean, I hope they don't create a problem with me solving this online. So anyway, let's get started. So section A, question 1. Which of the following statements applies to both electric fields and gravitational fields? Let's see. Each field causes a force on all particles. This is not true of the electric field because the electric field is proportional to charge, Q1, Q2. So this is not going to work. So that's false. Each field can cause an attractive or repulsive force. That's not true of the gravitational force. Field strength is proportional to the square of the distance from a point source. That's not true as well. So just by excluding all the other options, the correct choice is D, but it's also correct because it says that field strength is inversely proportional to the square of the distance from a point source. So that's right. Now, question 2. A mass is driven into oscillation and resonance takes place. Which of the following statements is not correct? The amplitude of oscillation of the mass is a maximum. That's correct. The frequency of oscillation of the mass is a maximum. Okay, that's suspicious because if you plot the amplitude with respect to frequency, okay, you will see that if the external forces frequency matches the natural frequency f naught of the system, then you're going to observe a maximum, but that's not the maximum frequency, so number B is not correct. Okay, letter B, I mean option 2, whatever. Let's move on. Energy is released when the fusion of low mass nuclei takes place. Okay, energy is also released when the fission of high mass nuclei takes place. Which row of the table shows the change in binding energy per nucleon for fusion and fission? Now, okay, if we plot the binding energy per nucleon as a function of the mass number, somewhere here is iron 56. Okay, and remember, you can also watch the videos that the graph looks like this. Okay, which means that when we fuse light nuclei, maybe we fuse this guy with this guy to produce this guy, then binding energy per nucleon for the fused nucleus increases. And if you have a heavy nucleus, maybe down here, that splits into two lighter nuclei, these two lighter nuclei are going to have a higher binding energy per nucleon. So the binding energy per nucleon also increases. So the only correct option is D. All right, I'm just gonna try to go over this fast as possible. Right, megaparsec is a unit of distance used by astronomers, and they give you that 1 megaparsec is 3.1 times 10 to the 22 meters. Okay. Recent estimates of the Hubble constant give a value of 74 kilometers per second per megaparsecs. Which of the following gives the age of the universe in seconds? Remember that the age of the universe is given by 1 over h naught. So they give us this parameter, which is the Hubble's constant, of course. So if we take the inverse, we have kilometers in the denominator, which we convert to meters. Okay, and in the numerator we have seconds, which we need, and then megaparsecs. Actually, let me erase that. So we have megaparsecs, and 1 megaparsec is, let's erase that, it's 3.1 times 10 to the 22 meters times seconds. So the correct option is, let's see, D. Okay, hope this makes sense. Basically, we do 1 over 74 megaparsecs seconds, and then we have kilometers. And all I did was to convert the kilometers to meters and convert the megaparsecs to meters as well. Okay, now question 5. On Earth, hydrogen is observed to emit a spectral line with a wavelength of 410 nanometers. The same spectral line is observed in the radiation received from a galaxy that is moving away from the Earth at a speed of 0.1 c. Which of the following is the wavelength of the spectral line in the radiation received from the galaxy? Okay, so we know that delta lambda over lambda lab is equal to V of the galaxy over C. So we can quickly calculate delta lambda to be 0.1 c over c. This gets cancelled times lambda in the lab, which is 410 nanometers. So delta lambda is 41 nanometers. Now, do we add or subtract? Is this a red shift or a blue shift? So if it's a blue shift, we have to subtract because the new wavelength as observed from the star is gonna be shorter. So let's see, what do they say? It says radiation received from a galaxy that is moving away. Okay, away means redshift. So because it's redshifted, it moves towards higher lambdas. So the new lambda is going to be lambda lab plus delta lambda, or 451 nanometers. The answer is A. Okay, hope this makes sense. Now, question 6, I think I'm going to use a clean page because we will need to do some calculations. Okay, let's add a new page and let's go back to read the question. In a laboratory, the background count rate is 22 counts per minute. Okay, the detector is placed 25 centimeters from a gamma source. The count rate recorded by the detector is 54 counts per minute. The detector is then placed 50 centimeters from the source. Which of the following is the expected number of counts per minute? Okay, so maybe we have a source over here. Okay, so that's the source. And we measure the radiation at a distance x equal to 25 centimeters, and then at a distance x again, so a total of 2x pretty much from the source of 50 centimeters. Okay, so here is my detector. All right, so how do we work out this problem? First of all, at the 25 centimeters, the count is 54 counts per minute, right? So the true count, so at 25 centimeters, we have 54 counts per minute. But that's the combined count from the source and the background. So we have to subtract the background, remember? So true counts from source are 54 minus 22, or 32 counts per minute. Okay, and that's at 25 centimeters. Now, if we double the distance, what do we have? Remember the radiation law? I is given by I naught over 4 pi times the distance squared. Okay, so at the 25 centimeters, we will have I, and I naught is the intensity of the radiation at the source. Okay, so let's call this 1 and let's call this 2. So I1 is going to be I naught over 4 pi times 25 squared. And then I2 is going to be I naught over 4 pi times 50 squared, right? Or I naught over 4, sorry, I1 over 4, I'm sorry. So it's going to be I1 over 4. And what is I1? 32 over 4, 8 counts per minute, okay? So what's going to be the count measured at distance 2 is going to be 8 counts per minute from the source, plus 22 because of the background radiation, which is the same everywhere. So I total is going to be 8 plus 22, or 30 counts per minute. Okay, if we go back here, the answer should be B, okay, because 54 minus 22 is 32 over 4, 8 plus 22, 30 counts per minute. So the correct answer is B. Okay, question 7. We will also need a clean page because we need some calculations as well. Okay, so a student used a detector to determine the intensity of radiation from a source of gamma radiation. After correcting for background, the intensity of radiation recorded by the detector was I naught. A lead sheet of thickness 2.5 centimeters was placed between the source and the detector. The corrected intensity of radiation recorded by the detector was now 0.5 I naught. The original lead sheet was replaced by a new lead sheet of thickness 7.5 centimeters. Which of the following was the corrected intensity of gamma radiation recorded by the detector? Okay. Now, this is from Unit 6, and I think I haven't, if I remember correctly, I didn't cover it in my videos because I still haven't decided what I'm going to do with Unit 6. But the idea is that if you have radiation, so you have some radiation I naught passing through a material of thickness X, then I prime, the radiation that exits, actually let's call this I, the radiation that exits the material is I, so I is given by I naught e to the minus mu times x. Mu is characteristic of the material and is independent of the thickness. So the same, if a material has a thickness of 10 meters, it's going to have the same mu as a material that has a thickness of 1 meter, okay? Mu is a constant of the material. And if I recall correctly, this is called the absorption coefficient. So we have enough information to actually calculate mu. So if the thickness is 2.5 centimeters, this is given to us, then we have half the radiation exiting the block. So 0.5 I naught should be equal to I naught e to the minus mu times x. So I naught gets cancelled. And x is actually, we have to replace with 2.5. Okay, and by the way, mu has dimensions of inverse meters, okay? Because this exponent is dimensionless. And in general, in physics, whenever you have variables appearing inside functions like the exponent, the sign, etc., those variables should give you dimensionless quantities because functions work with dimensionless quantities. I hope this makes sense. So I'm going to go over this fast. Actually, wait, 0.5 is 1 over e to the 2.5 mu. So mu is a ln of 2 over 2.5 centimeters. So mu for lead is 0.28 centimeters to the minus 1. Okay. I said it's measured in meters to the minus 1, but centimeters works as well. Now let's calculate what I is going to be if we replace the lead sheet with a sheet of thickness 7.5. So I prime is going to be I naught e to the minus mu x prime. Okay, so that's I naught e to the minus 0.28 times 7.5. And I recall how this is in centimeters to the minus 1. This is in centimeters, so these two cancel to get 0.13 I naught, okay, which is C. Okay, let's move to question 8. Two stars, X and Y, have the same luminosity. The graph shows how the intensity I of radiation received at Earth from star X and star Y varies with length lambda. Which of the following statements can be deduced from the graph? Okay, first of all, let's observe that both stars have the same luminosity. Okay, so we can immediately deduce that star X has a higher temperature than star Y due to the black body radiation curve, the Planck curve. Remember that stars that if I had a star like this, for example, that's going to have a lower temperature than star Y, and star Y will have a lower temperature than star X. Okay, so let me erase this. So let's read the the options. So only A and C have star X having a higher surface temperature. So B and D are immediately wrong. And then what do you think? Is the star X closer to Earth than star Y, or the other way around? It should be closer, right? Because we receive more intensity of radiation. Okay. So do I want to mention anything else here? No. Let's move to question 9. The graph shows how the displacement varies with time for an object performing simple harmonic motion. 4 graphs of quantity plotted against time for the same period of time are shown below. Okay, which graph shows how the velocity of the object varies with time? Remember that, okay, we can actually deduce from here that x is minus a and then cos omega t. Is that correct? The cosine, let me make it better. Okay, let me try to make better letters. So x is minus a cos omega t. Why is that? Because at t equals 0, we have cos of 0, which is 1. And this is negative a, right? Now, what is velocity? Is the first derivative. It's the first derivative of x, right? What's the derivative of cos minus sine? So we get omega a sine omega t, right? So what's that? That's at t equals 0, we have sine of 0 equal to 0. So it can only be d or c, but the velocity is positive, so it's d. The correct answer is d. You can also say that the velocity is displaced by pi over 2 compared to displacement. Or in other words, if that's your displacement, pi over 2, the oscillation is going to be there. Okay, so this is what it means to be shifted. Now, the acceleration is actually easier, which is question 10. Which graph shows how the acceleration of the object varies with time? Remember that acceleration is simply minus omega squared x, right? So we take the negative of whatever the displacement is, which is going to be this graph, right? So A. That's actually simpler. All right. Now let's move on to harder questions. Question 11 in section B, okay? The photograph shows a woman making a bungee jump. I would never be able to do this. I think I'm gonna die. I'm afraid of heights, even though I really like climbing. Not bouldering so much because I feel like I'm gonna fall and hit and hurt myself. I prefer rope climbing. So I haven't done it in years, but I like it. Okay, even though I'm afraid of heights, it doesn't make sense, but I like it. So, but bungee jumping, I would have no control, so I would feel terrified. So the photograph shows a woman making a bungee jump. The woman was attached to a platform high above the ground by an elastic rope. Okay, that's a key word. So elastic usually means you can approximate it using Hooke's law. Okay, so it behaves like a spring. Okay, keep that in mind. After reaching the lowest point of the bungee jump, the woman oscillated with simple harmonic motion of period 1.5 seconds. The woman returned to the platform to repeat the bungee jump. She was fastened to a second person. The same elastic rope, okay, that's the key. The same elastic rope was used for the bungee jump. After reaching the lowest point of the bungee jump, the two people oscillated with simple harmonic motion. Calculate the period of oscillation of the two people. Okay. Since the rope is elastic, we are going to assume it follows Hooke's law. So the period of oscillation is simply 2 pi times the square root of the mass of the woman over k. Okay. But we don't know. Actually, let me use a clean page. Can I cut this? Yes. Oops. I said cut. Okay, good. And let's move to a clean page. Okay. Now paste. Paste. Okay. Great. I haven't done this before. All right. So the period of oscillation is 2 pi times the square root of the mass of the woman over k. The new period is going to be 2 pi times the square root of the mass of the woman plus the mass of the second person over k. We don't know k, so let's get rid of it. How? Just divide the two equations. So t over t prime is 2 pi times the square root of the mass of the woman over k over 2 pi times the square root of the mass of the woman plus the mass of the second person over k. 2 pi gets cancelled, k gets cancelled. Both k's are in the square root, so we can cancel them. So t over t prime is equal to the square root of the mass of the woman over the mass of the woman plus the mass of the second person. So t prime is equal to t times the mass of the woman over the mass of the woman plus the mass of the second person, or 1.5 seconds times the square root of 67 plus 72 over 67. And if we solve that, we find 2.16 seconds. Okay. I think this was straightforward, so let's move on. Okay, this is a writing problem now. The photograph shows a student observing the tracks of alpha particles and beta particles in a cloud chamber. The particles ionize the air as they pass through the cloud chamber. Liquid droplets form around the ions, and the droplets form visible tracks. The alpha particle tracks are thick and straight. The beta particle tracks are thin and twisted. Okay? The student gives the following explanation for the appearance of the tracks. The alpha particle tracks are thick because the alpha particles are massive particles. I guess this is the first statement. Okay, so that's statement one. The tracks are straight because the alpha particles are highly ionizing. That's statement two. The beta particles cause a similar amount of ionization as the alpha particles. That's statement three. The beta particle tracks are thin and twisted because beta particles are much less massive than alpha particles. That's statement 4. I think I mentioned it in a previous video. I think I only have one video where I go over a past paper. But the rule of thumb is if a question takes 4 marks, it should take about 4 minutes to solve. And also it will involve 4 statements if it's a writing problem. If it's 6 marks and it's a writing problem, you usually have to provide 6 pieces of evidence or 6 statements and so on. So for the questions in section A, for example, they take 1 point, so they should take you about 1 minute. But you shouldn't panic, like some problems are a little bit harder, so they might take you longer. But for example, question 11 took us maybe 3 minutes to solve, so 3 marks, okay? Now, we have to criticize the student's explanation. Let's start with the first statement. Okay, 1. The alpha particle tracks are thick because the alpha particles are massive particles. No, that's wrong. So, wrong. The alpha particle tracks are thick because alpha particles with z equal to plus 2e are highly ionizing. So they leave thick tracks by ionizing the air. Now statement 2, the tracks are straight because the alpha particles are highly ionizing. So that's also wrong. The correct answer is that alpha particles are massive and their mass is approximately equal to 4 atomic mass units. Why is that? Because remember, the alpha particles are helium-4 nuclei. Actually, you write them as alpha 4-2. So the rule of thumb is that a nucleus has a mass of about whatever the mass number is times 1 atomic mass unit, so 4U. So for uranium-235, the mass is approximately 235 U's, but usually in calculations where you need the mass, it's usually given to you with more accuracy than that, okay? Now, alpha particles are massive with a mass of 4U, thus they are not easily deflected. So they move in straight lines. And a good way to think about this is think of a really large, I don't know, a cannonball, for example. It's not going to be easily deflected by air or something, right? Because it's massive and it moves with some speed. Whereas if you have a ping pong ball representing the electron, actually a basketball ball is better, maybe. So it's not easy to deflect a basketball ball once you throw it, right? But if you throw a ping pong ball into the air, it's gonna get deflected really easily. So the electron is about 2,000 times lighter than the proton. So 8,000 times lighter than the alpha particles. So electrons get easily deflected, okay? Oops, we have 2 more statements. Let's use a clean page. Statement 3. The beta particles cause a similar amount of ionization as the alpha particles. That's wrong. Wrong, because beta particles have a charge of minus E. So they are less ionizing than alpha particles. And the final statement is that the beta particle tracks are thin and twisted because beta particles are much less massive than alpha particles. That's actually correct. So that's the only correct statement. So correct. Beta particles are light. So they get deflected easily. How do they get deflected? From the interactions they have with other electrons, with nuclei, etc. Okay. Right. Now let's move to question 13. A satellite of mass 6.5 times 10 to the 3 kilograms is initially at the surface of the Earth. The satellite is launched into a circular orbit of radius 4.22 times 10 to the 7 meters. Calculate the change in gravitational potential energy of the satellite. Okay, so it's good to work these problems in two steps. First, find the gravitational potential, and then find the difference in gravitational potential, and then multiply with the mass of the satellite to find the change in gravitational potential energy. Okay, so let's find the gravitational potential at the surface of the Earth. That's given by G times the mass of the Earth times over the radius of the Earth. So that's minus 6.67 times 10 to the minus 11 times 5.92 times 10 to the 6. And then we have, can I write there? Actually, let's also cut this and move to a clean page. So cut, and then let's use a clean page. Paste. Okay. Right, so I think I mentioned it in other videos, but I usually put all the units to the left, all the numbers to the left and the units to the right. So let's put the units over here because I ran out of space. So we have newtons times meter squared times kilograms to the minus 2. That comes from, these are the units that come from G, times kilograms, that's for the mass of the Earth. And in the denominator, we have 6.37 times 10 to the 6. And then that's meters in the denominator. So that gets cancelled. This is minus 1. And then we have newtons times meters. That gives us joules. And then we have kilograms in the denominator. So the final answer is minus 62.62 times 10 to the 6 joules per kilogram. Now, the potential at wherever the satellite is, at, let's call it point R, is minus G times the mass of the Earth over R. So that's minus 6.67 times 10 to the negative 11 times 5.92 times 10 to the 6 over 9.45 times, sorry, I don't know where I found that, 4.22 times 10 to the 7, and this is joules per kilogram. We established that, so we find minus 9.45 times 10 to the 6 joules per kilogram. All right. Now, delta V is V final minus V initial. What's V final? The gravitational potential at wherever the satellite is minus the gravitational potential at the surface of the planet. So notice that this is going to give us a positive number. That's important, and we'll see why. So minus 9.45 times 10 to the 6 minus of minus 62.62 times 10 to the 6, and that's joules per kilogram, which gives us 53.17 times 10 to the 6 joules per kilogram. I have the mark scheme somewhere. Let me check quickly that this is correct. Just a second. Yeah, that looks okay. Now, the change in gravitational potential energy is then mass of the satellite times delta V. So 6.5 times 10 to the third kilograms times 53.17 times 10 to the 6. And then we have joules per kilogram times kilogram, which gets cancelled. It gives us 3.46 times 10 to the 11 joules. Okay, which is positive. Why? Because because the satellite has a higher potential, gravitational potential, at its orbit than at the Earth. And you can see that because if imagine lifting a weight of the Earth, right? That weight gains gravitational potential energy, right? Because then if we throw it, that gravitational potential energy gets converted to kinetic energy, right? So it falls. So the same is true about the satellite, all right? I think we will need a second page as well, because there is a part B. The satellite is in its orbit, the satellite is in orbit above the equator. Deduce whether the satellite would appear to be stationary above the surface of the Earth. And they give you that the period of rotation of Earth about its axis is 8.64 times 10 to the 4 seconds. Geostationary satellites, by the way, move above the equator, and their period of rotation is 24 hours pretty much, okay? So they appear stationary. Now let's go calculate that. So we need to find the period pretty much. How do we find that? Remember that if this is the Earth and this is the satellite, and r is measured from the center of the Earth, then what makes this move in a circular orbit? The gravitational pull of F, let's call it gravity, okay? So F gravity is what makes it go in a circular orbit. And in circular orbits, we have the velocity being tangent to the circle, right? So F gravity should be equal to m v squared over r, okay? R is shown, V is shown, and the gravitational force is shown. What's the gravitational force? It's given by Newton's law of gravity. So G, mass of the Earth, mass of the satellite, over r squared should be equal to the mass of the satellite, V squared, over r, okay? And then the mass gets cancelled, okay? Then, and what's the best way to show this? The velocity, I mean, it goes into a circular orbit, right? Velocity, velocity. And the magnitude of this velocity is constant, okay? So we can calculate, so in one period, where one period represents one full circle, remember that velocity is distance per time. What in one period or in one full rotation, the satellite completes a full circle of radius 2 pi r, right? So v squared is simply 4 pi squared r squared over t squared. So if we combine these two, and I'm afraid we are going to need another page, we find g me over r squared over r, actually, sorry, because you can cancel this, okay, is equal to 4 pi squared r squared over t squared. You have to prove this at all times, guys, by the way, okay? So t squared is 4 pi squared r cubed over g me. And we can plug in numbers here instead of taking the square root. It's a little bit cleaner. I like to do it that way. So t squared is 4 times 9.87, that's pi squared, okay, times 4.22 times 10 to the 7 cubed. So always do that. It's easier. When you are dealing with variables that get cubed or squared or raised to a power in general, use parentheses, okay? It's cleaner. It avoids confusion. So the units are meters to the cubed from the radius, okay? And then we have g in the denominator, which is 6.67 times 10 to the minus 11. And then the mass of the Earth, 5.98 times 10 to the 24. The mass of the Earth is in kilograms. G is given in, let me think, newtons meter squared over kilograms squared. Okay, so this gets cancelled, this gets cancelled, and what else? Let me carry on. So this is equal to 7.44 times 10 to the 9, and we have meters, kilograms, and we'll have newtons in the denominator, but 1 newton is 1 kilogram times meters per second square, so everything gets cancelled except second square, so that makes sense because we are calculating t squared, okay? And I remind you that 1 newton is 1 meters times second square, meters over second square times, sorry, I think I confused you. So 1 newton is 1 kilograms times meters over second squared. Why is that? Because F is MA, right? So, and if we take the units, remember that when we use square brackets, we mean the dimension of that quantity. So what's the dimensions of force? Newtons, what's the dimension? The SI dimensions. What's the SI units for mass? That's kilograms. What's the SI units for acceleration? Meters per second squared. So you see where I got things from. Anyway, if we take the square root of that, we find 8.63 times 10 to the 4 seconds, which almost matches the period of rotation of Earth about its axis. So yes, it will appear stationary. Okay, let's move to question 14. Astronomers use a variety of methods to determine the distances to astronomical objects. Explain why trigonometric parallax can only be used to determine the distance to objects that are relatively close to Earth. So let's refresh our memory. You don't have to do this in the test, but what's the parallax based on? So if you have the Sun and you have the Earth now and in 6 months, okay, so 6 months, then this distance is 1 astronomical unit, and this distance is also 1 astronomical unit. Now, we are interested, say, in a star that is at a distance d away from us, okay, and we observe it, let's say now, and then in 6 months, and we notice that it moves compared to a background of stable stars. So what do we mean by stable? They are so far away that they appear to not move at all during those 6 months, whereas the apparent position of this star that we are interested in moves within those 6 months. So let's call this the background. BG means background of stable distant stars. All right, so let's go actually answer the question. So parallax is that angle to theta. So the parallax is equal to 2 theta. Okay, now let's write this down. The method is based on measuring the parallax angle. Actually, I'm going to run out of space, so I'm going to move to the clean page. Okay, let's do cut and paste. Okay. So the method is based on measuring 2 theta, okay? That's the parallax. The star needs to be close enough not closed, close, sorry, so that its apparent position with respect to a background of distant stars, of distant stationary actually, changes within a 6-month period. Otherwise, if this actually no, delete otherwise. If the star is too far away, 2 theta is going to be too small to be measured. Okay, and in other words, it will also appear stationary. Okay, so we won't be able to see any parallax. Okay, let's move to question B. For objects that are not close to the Earth, the method of standard candles is used. State what is meant by a standard candle. So standard candles are stars with known luminosity. Such as type 1 supernova. We mentioned that before. Describe how the method of standard candles is used to determine the distance to a distant star cluster. So, once a standard candle is found, you need to measure the intensity of radiation received from that star on Earth. And I remind you that's the intensity in watts per square meters. Okay? Once I is found, use I equals to the luminosity, equals to the luminosity over 4 pi d squared to find d. Okay, because you know the luminosity, you know the intensity. Okay, so that's it. Okay, next question. Okay, let's move on to question 15. The body of a racing car is connected to the wheels of the racing car by a suspension system as shown. They show the wheels, the suspension system, and the racing body car. By the way, this is a Formula One car from the 70s. I think it's a Lotus car. Let's go see. Let's check it out. Sorry for this. So I think it's a Lotus Formula One. Formula One. Let's do 70s. I'm pretty sure it's that. So images. Do you see anything like that? Maybe 60s. Let's do 60s. 60s. Yes, that's exactly it. Yeah, there it is. So, and yeah, I mean, it makes sense that they use this because it's this is an English test, and this is a famous team from back in the day. Okay. Which I think Lotus cars still exist. Anyway, let me know in the comments. Anyway, let's go back to this. So we have a racing car. When the body of the racing car is displaced vertically from its equilibrium position, the suspension system causes the car to oscillate with simple harmonic motion. Okay, don't get confused. What they mean here is that if this is the wheel, okay, and we see the side of the car moves this way, but the oscillation is in this direction. This is the vertical direction, okay? So up and down pretty much, okay? State the conditions for an object to oscillate with simple harmonic motion. Start by writing that A is minus omega squared r. So we need the acceleration. Actually, let's say alpha, the acceleration A, is proportional to the displacement from the equilibrium position and points towards it. Okay, so we have an acceleration that tends to bring the body back to the equilibrium position. Question B. The graph shows how the vertical displacement y of the car body varies with time t. And notice that we are talking about a 3 centimeter vertical displacement. So, I mean, this is the amplitude, okay? So that's nothing. I mean, remember when I told you that don't get confused by the motion of the car in a straight line because you are talking about the vertical displacement. So that's what I meant. All right. Determine the maximum velocity of the car body for 4 marks. So I think that's a gift pretty much because Vmax is omega times the amplitude, right? What is omega? 2 pi over the period times the amplitude. We can come back to the graph and read off the amplitude. So this is the amplitude, 3 centimeters. And the period we can measure from here to here. That's 1 period. And if we read it off, it's 0.6 minus 0.4. That's minus 0.2 minus, it gives us 0.4 seconds. I'm sorry. So we get 2 pi times 0.03, because I converted centimeters into meters, over 0.4 seconds yields 0.47 meters per second. Okay. Explain how damping causes the amplitude of oscillation of the car body to decrease. So what is damping? Damping is a resistive force. It's a force that acts in the opposite direction than the vertical velocity. Okay, so because we can answer this by stating that because a force acting in the opposite direction from the vertical velocity, in the opposite direction of the vertical velocity, it's better, of the vertical velocity, energy is absorbed as heat because work is done against resistive forces. Okay, this can be an answer, but with these writing problems there are many different ways to answer the question. All right, let's now move to question 16. I think we're gonna need a clean page because if I remember, it's a long problem when I solved it. A food delivery company uses ice packs, to keep food cold during delivery. Each ice pack consists of a block of ice in a waterproof bag. Each block of ice is initially rectangular as shown, and they show a scheme there. Water at 0 degrees Celsius is frozen to form the block of ice. The block is cooled to a temperature of minus 7.5 Celsius. The block is then sealed in the waterproof bag. Determine the energy transfer to form the ice block and reduce its temperature to minus 7.5 Celsius. Okay, so this is a two-stage process, because if this is the ice pack, initially you have water at 0 degrees Celsius that freezes into ice. So let's make the ice to look solid. Okay, so this is water, this is ice at 0 degrees Celsius as well, and then we have to reduce the temperature of ice to minus 7.5 degrees Celsius. Okay, so this is still ice. Okay, so we need to use the latent heat of fusion of water. We need to calculate how much energy we have to spend there, and how much more energy we need to spend to reduce the temperature to minus 7.5 Celsius. Okay, and also another assumption is that we will need the mass of water, and to calculate that we will assume that the density of ice and the density of water is the same, because that's the only information given to us. Okay, let's go calculate the volume to begin with of that block. So that's 0.15 meters times 0.015 meters, which is 1.5 centimeters, times 0.25, and this is meters cubed. So the volume of the block is just 5.63 times 10 to the negative 4 cubic meters. Now density is mass per volume, so mass is density times volume. The density is 920 times 5.20, oops. The density is 920 kilograms per cubic meter times 5.63 times 10 to the negative 4. And let's see, let's cut this. Cut. And let's move to the new page. Okay. So kilograms per cubic meters times cubic meters. So this gets cancelled. And we find the mass to be 0.52 kilograms, so half a kilo. Now, the energy spent to freeze this water is going to be delta M, this mass, times the latent heat of fusion, which is 0.52 times 3.4 times 10 to the 5 joules per kilogram times kilograms. These cancel out nicely to give us 175 950 joules. Okay, so that's the energy needed to freeze the water to ice. And then we need to reduce the temperature of ice. So for that, we are going to use delta E is C M delta theta. The specific heat capacity of ice is given, so we simply have to multiply numbers. 2100 times 0.52 times the change in temperature. In general, when you deal with heat and temperature and stuff like that, it's good to use kelvins, but here, because it's a difference in temperature, a difference in temperature in Celsius is the same as the difference in temperature in Kelvin, so that's fine. So we multiply with 7.5, and this yields 8,190 joules. So delta E total is just 184.140 joules, where I add this and this. Okay, so that's the answer. Okay, there is a part B to this question. The website of the delivery company includes the following statement. If the ice has melted by the time you receive your delivery, this means that energy from the ice has been used to keep the food cold. Explain why this statement, the statement made by the company, is not correct. So it's all wrong, right? Because energy is only transferred from a hot body to a cold body. This is also known as the zeroth law of thermodynamics. So what they state there is totally wrong. And let's explain why. Heat can only flow from a hotter to a colder body. So heat is transferred from the hot food to the ice pack and melts the ice, and not the other way around. Okay, I hope this makes sense. Now, let's go to question 17. The Gaia globe is a three-dimensional model of the Earth as shown. The inflated globe is suspended from above and is able to rotate. The globe is filled with nitrogen gas. When fully inflated, the globe has a radius of 3.5 meters. Is this a real thing? Let's check. Curious. So let's do, where's the keyboard? Gaia globe sphere. Let's see. It's a sculpture. Okay. You can check it out later, guys, but let's go back to the problem. So, calculate the mass of nitrogen gas needed to exert a pressure of 1.12 times 10 to the 5 pascals inside the globe at a temperature of 22 degrees Celsius. And they provide the mass of a nitrogen molecule, which is convenient. All right, so what do? We use, okay, they give us pressure, they give us the radius, which can be used to calculate the volume of a sphere, and they give us the temperature. So we use PV equals to NKT, the ideal gas law, and we need to calculate N, the number of molecules inside that globe. Okay, so that's PV over KT. Okay, now let's plug in numbers. 1.12 times 10 to the 5. 1 Pascal is 1 Newton per square meter, times the volume, which is the volume of a sphere is 4/3 pi times the radius cubed. The radius is 3.5 cubed meters cubed. Don't forget to cube your units as well, okay? And then in the denominator, we have 1.38 times 10 to the minus 23 for actually for Professor Boltzmann's constant, given in joules per Kelvin, okay, times the temperature. Don't forget to convert your temperature to kelvins. Okay, how do you do that? That's 273 plus 22 Kelvin. Okay, kelvins with kelvins cancel, meters squared with meters cubed cancel. Newtons times meters gives us a joule, which cancels with joules. So we get a dimensionless number, all right? Which makes sense because this is the number of molecules, all right? And I will actually need to do the calculations because I haven't worked on this. So 1.12, I'm using my calculator, times 10 to the 5 times 4/3 times pi times 3.5 cubed, okay, over 1.38 times 10 to the minus 23 over 295, which is the temperature, gives 4.94. So 4.94 times 10 to the 27 molecules. Let me check the mark scheme. This is problem 17. Okay. Yes, that's correct for the number of molecules. But they say that we have to calculate the mass. So the mass of nitrogen gas is going to be N times the mass of one molecule, which is nitrogen, okay? So the mass is that number, this one, times this one. Let me calculate that, times 4.67 times 10 to the minus 26. Turns out that that is 230.7 kilograms, okay? That's quite heavy, but this is a 3.5 meters radius globe, which means that the diameter is 7 meters. So that's like 2 floors, okay? So that's a huge sphere. Hope this makes sense. Now, the globe rotates with an angular velocity of 2.76 times 10 to the negative 2 radians per second. Calculate the time taken for the globe to make one complete rotation. So omega is 2 pi over tau. So tau is, the period is 2 pi over omega. This is a gift question actually. So 2 times 3.14 over 2.76 times 10 to the negative 2 radians per second, and this is radians from the pi. So the period ends up being 227.7 seconds. So that's about 4 minutes. 4 times 60 is 240. Yeah, something like that. Is this correct? Yes. Okay. A solid sphere has the same diameter as the Gaia globe. Calculate the mass of the sphere that will give a value of G at its surface of 9.8 newtons per kilogram. Okay, so it should be really massive, right? So G is G times the mass over R squared. Okay, so we are thinking about the way to think about that is that we will need a lot of mass for a sphere of radius 3.5 meters to have the same gravity as the gravity of the whole planet, which has a radius of 6 million meters, is it? Radius of Earth, I'm sorry. Radius of Earth. 6,307. So yeah, 6 million meters pretty much. Okay, let's go back. So we need to solve for mass. Mass is G times R squared over G. I'm gonna come down here. So 9.8 times 3.5 squared over 6.67 times 10 to the negative 11. Since we are using SI units for everything, this ends up being kilograms. I'm being lazy now. So the mass should be 1.82 times 10 to the 12 kilograms. So that's a massive mass for a sphere of 3.5 meters, okay? So actually, this is 10 to the 12 times lighter than the Earth, but this is a massive, this will be a massive sphere, okay? Don't know why they had this question, but I hope things make sense. Now, question 18. The Hertzsprung-Russell diagram shows the relationship between the luminosity and the surface temperature of a range of stars. The Sun is a main sequence star. Label the position of the Sun on the diagram with the letter S. Okay, so on the vertical axis, we have the luminosity over the luminosity of the Sun. So, okay, this is the luminosity of the Sun. So, the luminosity of the Sun is 1. And the surface temperature of the Sun is, do you guys remember? It's something you should remember, actually, to be able to find the answer here, because it's about 6,000 degrees. So somewhere here, we will put, actually, sorry, let's do undo, and then undo. So somewhere, oops, somewhere here. So that's S. That's where the Sun is, okay? In the final stages of the Sun evolution, it will become a white dwarf star. Draw on the diagram a possible path of the Sun as it evolves to a white dwarf star. So, okay. So it will start in the main sequence here. It will turn into a red giant. Red giants are over there. You have to remember this diagram, by the way. So, red giants. So these are more luminous stars, okay? But they have a lower surface temperature. This is a result of the fact that they are massive. They have a much larger radius, so radiation spreads outwards, reducing the temperature, okay? And then the final stage is a white dwarf, which is a star with, so white dwarf. These are stars with a very high surface temperature, but not very luminous, and also small, okay? Small in size. Question B, it's a long writing problem. Describe the stages in the evolution of the Sun from a main sequence star to a white dwarf star, okay? So that's 6 points, meaning that we have to provide about 6 points, like 6 statements, 6 different statements. Let's see. Let's start by stating the obvious. In the main sequence stage, the Sun burns hydrogen, and fusion balances the energy from the fusion balances the gravitational energy that tends to collapse the star. Okay, next stage. Hydrogen burning. Once hydrogen decreases, hydrogen burning stops. Gravity takes over and collapses the star. Gravity makes the star collapse, increasing the temperature. Hence, helium burning starts. And the star expands. And the sun will expand because fusion energy becomes larger than gravity. Okay, when the fusion of helium stops, the star collapses due to gravity, which is now greater than the fusion energy. So the gravitational energy is larger than the fusion energy. And a white dwarf is formed. Why doesn't the white dwarf collapse? Because of the Pauli principle. I mentioned it in one of my videos. So there is not enough mass to push against the electrons in the star, so the collapse stops, and all white dwarfs in the universe are the same, okay? About the same. Now, explain why the sun will stay on the main sequence for a much greater time than the most massive main sequence stars. As the joke goes, the star that burns the brightest shines for a, what is the saying? Okay, okay. Explain why the sun will stay on the main sequence for a much greater time than the most massive main sequence stars. So, massive stars in the main sequence have significantly larger temperatures which causes hydrogen to fuse at a higher rate and thus run out. Okay, so it runs out of fuel faster, pretty much. Okay, next question. I think Tau Ceti is how you pronounce it, is a main sequence star similar to the Sun. Several planets orbit Tau Ceti. Question A, part 1. The spectrum of electromagnetic radiation emitted by tau SETI has a minimum intensity at the frequency of 5.5, a maximum intensity at the frequency of 5.5 times 10 to the 14 hertz. Show that the surface temperature of tau SETI is about 5,300 Kelvin. Okay, Wien's law tells us that lambda peak times the temperature is 2.898 times 10 to the negative 3 meters Kelvin, and then speed of light is equal to lambda times f. So combining these two, we find tau to be 2.898 times 10 to the negative 3 times the frequency, which is 5.3 times 10 to the 14 over 3 times 10 to the 8 for the speed, and this is in kelvins, and this will give you 5,120 Kelvin. This is what I found. Calculate the average kinetic energy of gas atoms at the surface of tau SETI. The energy is 3½ kT, and if we plug in numbers, we find 1.06 times 10 to the negative 19 joules. Simple as that. Moving on. I don't know how that's pronounced. Let's call it Ida or Eta. I don't know. Let's say Ida is a planet in orbit around tau SETI. A scientist suggests that Ida receives the same intensity of light from tau SETI as the Earth receives from the Sun. Evaluate the accuracy of this suggestion. And they give you the radius of tau SETI, the distance between Ida and tau SETI, and the intensity of light received at the surface of Ida. That's wrong because it's mentioned in the beginning. So this is actually the Sun. Okay. Now, how do we work this out? We have to find the luminosity first, which is equal to sigma A T to the 4th power, and sigma is a constant, 5.67 times 10 to the minus 8. I'm being lazy with the units because we are using SI units and everything works out to the proper unit we need. The radius of a sphere is 4 pi times the radius squared, and the radius is 5.52 times 10 to the 8 squared. And then we have to use the temperature to the 5th power, to the 4th power, I'm sorry. So that's 1.49 times 10 to the 26 watts. But then we have to find the intensity of radiation at the surface of Ida, which is equal to the luminosity over 4 pi d squared. And that's 1.49 times 10 to the 26 watts over 4 pi times that distance given over here squared, 8.05 times 10 to the 10 squared meter squared. This gives 1.83 times 10 to the 4th watts meters to the minus 2, which is 1830 watts per square meter, which is larger than what the Earth receives from the Sun. Okay, so the statement is incorrect. So, incorrect statement. Okay, that was question 19. And the final question is question 20. By the way, I don't know if the tests follow the trends of scientific research and scientific inquiry, but we are living in an era in which there is a new space race kind of taking off. I mean, you have SpaceX, you have NASA trying to put new telescopes. They actually put James Webb telescope was put into orbit. Then you have China having a new mission trying to reach the moon, I think. India has a space program now. Then you have the European Space Agency. So there are things going on, so maybe that's why they have too many questions related to space. So this is just a hypothesis, I don't know. So the space probe Galileo was sent into space to study the planet Jupiter. The space probe was powered using plutonium-238. Plutonium-238 decays to an isotope of uranium by emitting an alpha particle. Complete the nuclear equation for the decay of plutonium-238. So whatever is here should add up in the left-hand side. So alpha particle has 4, a mass number of 4, and a Z of 2. So 92 plus 2 gives us 94 for plutonium. And then we need uranium to be uranium-235, so that 234 plus 4 gives us 238. Okay. Show that the energy released in the decay of one nucleus of plutonium-238 is about 5.7 MeVs. Okay, this will take some time, but we have to find the mass difference, which is the mass of the parents, which is mass of plutonium, minus the mass of the daughters, which is uranium, minus alpha. So we have 3.95 16 times 10 to the negative 25 minus 3.8251 times 10 to the minus 25 minus 6.6399 times 10 to the negative 27. So delta M ends up to be 1.01 times 10 to the minus 29 kilograms. By the way, this has to be positive. If you find a negative number, you probably have to switch the order in which you subtract the nuclei, the masses of the nuclei, sorry. So delta E is delta M C squared from Albert Einstein. So 1.01 times 10 to the negative 29 times 3 times 10 to the 8 squared gives us 9.09 times 10 to the negative 13 joules. And we have to divide by 1.6 times 10 to the negative 19 joules times EV to the minus 1 to get the same thing in EVs, and we find 5.68 times 10 to the 6 EVs, which is about 5.7 MeVs. I went over this a little bit fast. I hope it makes sense. Part 2. When the space probe was launched, the decay of plutonium-238 produced a power of 550 watts. A website states that there was 1 kilogram of plutonium-238 when the space probe was launched. Deduce whether the website statement is accurate. So they give you the number of atoms in 0.238 kilograms of plutonium as Avogadro's number, pretty much, 6 times 10 to the 23rd. Half-life of plutonium is 87.7 years, and they give you what a year is in seconds. So let's find how many atoms there are, first of all. So N is 1 kilogram, and then we have 0.228 kilograms per 6 times 10 to the 23 atoms. Okay, we divide kilograms with kilograms, so that gets cancelled. So that's 2.52 times 10 to the 24 atoms. Okay. Then recall that activity is lambda times the number of nuclei. Then lambda is not given, but we know the half-life, so that's ln2 over t1 half times the number we just found. And if we multiply, we find 6.32 times 10 to the 14 seconds to the minus 1 for the activity. And then power is equal to the activity times the energy from one decay, which we calculated earlier. It's over here in joules. Oops, let me use a red color. So that's the energy you need. Okay, I'm going a little bit fast. So 9.09 times 10 to the negative 13 times the activity 6.32 times 10 to the 14 gives us 575 watts. Okay, so the website is accurate. So I'm gonna write it here, accurate. Now, the space probe took 74 months to travel to Jupiter. Calculate the power produced when the space probe arrived at Jupiter due to the decay of plutonium 238. So, whatever is true about the decay, remember that n is n naught e to the minus lambda t. Whatever is true for radioactive decay is true of activity, and it's also true of power. So power is p naught e to the minus lambda t. So the power is going to be equal to p naught e to the minus lambda. We have to use ln of 2 times time over t1 half. So we have 575 times e to the minus ln of 2. Then the time is 74 months times 2.63 times 10 to the 6 over t1 half, which is 87.7 years, right? Times 3.15 times 10 to the 7. The calculation is going to give you, I'm going to read it off the mark scheme because I'm lazy to do this calculation. I feel lazy. I'm sorry, guys. It happens to teachers as well as students. Okay. Let's see. So 548 watts. So not too bad. Okay. Jupiter is much farther away from the sun than Mars is. A space probe to Mars was powered by solar cells. Suggest why solar cells were not suitable for a space probe traveling to Jupiter. Okay, remember that the intensity falls off as intensity of, actually let's write luminosity because we are dealing with the sun. So the intensity is going to be equal to the luminosity of the sun over 4 pi d squared. So Jupiter is much further away, so less sunlight, less energy. Okay, so it's not gonna work. And this is it, guys. This is May 2025 Unit 5 test for Edexcel International A-Level Physics. Let me know what you think in the comments. I'm gonna try to make more videos, and I'm actually gonna start uploading videos related to physics, like university level and further beyond. We'll see. Anyway, thanks guys for watching. I hope this is useful. Bye.